example, in saturating organic fatty acids and, for example, making fats from oils, right? And if you actually take normal oil and you throw in some zinc, and some nickel, rainy nickel, any of these metals, and you add hydrogen to it, within no time at all, you can actually see it turning to a fat, right? And there is, in fact, a very nice video on YouTube where someone actually does this so you can see it. So it's a very important industrial process, and understanding it is essential. And I would say up until the early 1960s, hydrogenation was a process that was exclusively carried out by heterogeneous systems, okay? And like you just mentioned, one of these very interesting systems is so-called Lindlar hydrogenation. The mechanism of this hydrogenation is in fact to date not fully understood, but it involves some sort of poisoning of the catalyst surface by taking essentially palladium, which is absorbed onto or supported on a calcium carbonate surface, and adding quinoline and lead acetate to it. This effectively causes some sort of poisoning in the palladium surface to such an extent that it is not as powerful a hydrogenation catalyst. And what you can do with Lindlar hydrogenation, which is heterogeneous catalysis, is, for example, only hydrogenate an alkyne to an alkene. The other advantage of Lindlar hydrogenation is that you have, it's a stereochemically controlled reaction. And you exclusively always end up with, if you react an alkyne with hydrogen, you end up with a cis-configured alkene. Okay? So this is something that one shouldn't forget. It is a very important and useful tool to have if you want to access cis-alkenes from alkynes. So remember now, just try and keep all of these reactions in your head. We've just looked at Sonogashira coupling. So let's say if you want to make a natural product that has necessarily cis stereochemistry of an alkene, what you could sort of do is do a Sonogashira coupling and then a Lindlar hydrogenation. You know, so one must always think of combining these things and look at the holistic picture. Now, as I said, hydrogenation was really widely used, and in the early 1960s, basically, there were some people looking at trying to make homogeneous catalysts of hydrogenation, and some people were quite successful in this regard. But the catalysts that they made were not nearly as active as these heterogeneous systems that are so reactive that, for example, as you see with a Lindlar catalyst, just to sort of tame it, you have to in fact poison it. If you don't poison it, it goes all the way, it reacts all the way through to the saturated alkane. So in the mid-1960s, Jeffrey Wilkinson, who some of you may know won a Nobel Prize in 1973, which he shared with Fisher. In fact, he didn't win a Nobel Prize for the work that he did on hydrogenation catalysis. He won it for the work that he did on the structural elucidation of sandwich compounds. But anyway, he was from Imperial College. He was an excellent organometallic chemist. And he synthesized, him and his group synthesized this deceptively simple rhodium-1 compound, right? Rhodium tris-triphenylphosphine chloride. What does this remind you of? Yes. Viscous complex, right, which is iridium bis-triphenylphosphine chloride CO. The electron count and the electron configuration of the two complexes is essentially the same. This is how to synthesize it. If you basically take rhodium chloride, it's typically hydrated, and you react it with triphenylphosphine in the presence of, you'd carry out the reaction in methanol typically, and you have actually a redox reaction taking place, right? You have a redox reaction taking place. In fact, the methanol gets oxidized up to methanol, right? So it in fact acts as a sort of, it's a redox reaction, and you go from rhodium-3 to rhodium-1. The phosphine gets oxidized, okay? The phosphine gets oxidized and you form these products. That's a very simple reaction, right? In fact, it's It's a reaction I might build into the 2000 inorganic practical next year, because I think it's a nice compound to make, and then you can maybe do some hydrogenation reactions with it. The problem, of course, is rhodium is pretty expensive. But this compound was an important stepping stone in the development of homogeneous catalysts of hydrogenation, for hydrogenation, because it was the first system where the activity started approaching or approached or matched the activities that you see with the heterogeneous catalysts that were being employed up until that time. Rainy nickel, for example, palladium C, Lindlar hydrogenation, etc. So that's why this is an important compound and is widely used today to do hydrogenation reactions of alkenes. This is the structure. It's square planar, right? Very similar to Vasca's compound. You can see it's enormously congested sterically with these sterically demanding triphenylphosphines. This is a space-filling model here. Now, I actually think it's quite amazing that he had the insight to try and to see that this could be used as a hydrogenation catalyst. Because if I had synthesized a molecule like that, I would say, well, it's a dead duck, right? But in fact, what happens is this happens, okay? So you have, you start off with a catalyst precursor. It undergoes triphenylphosphine loss, okay? Dissociation, which is what we often see as a first step in many of these reactions. Also what we just saw in the CC coupling reaction. And this generates then a hot 14 valence electron rhodium-1 precursor. Now remember, you're doing hydrogenation, let's say, of an alkene. Oxidative addition takes place, and you end up with cis stereochemistry of the oxidatively added H2. Why that? Why is it cis configured? Because it proceeds in a concerted fashion. Remember when we were looking at Vasca's compound many moons ago, right? I said to you guys, this is an important compound because it's going to come back later. Understanding its chemistry is important because it's an excellent model. And here you see it. Here it is. It reacts, this compound can be thought of to be electronically analogous to the Vasca's compound. Now, if Vasca reacts with hydrogen, what happens? It proceeds in a concerted fashion. We'll see that in a moment. I have a nice slide to illustrate just to remind us all why that is the case. The other possibility with a Vasca's compound was that we reacted it, for example, with methyl iodide. Remember? In which case we end up with a trans stereochemistry. It is also an oxidative addition reaction, but we end up with a trans stereochemistry because... Yes, because we have an ionic mechanism and something that resembles an SN1 type mechanism in organic chemistry. Here we have necessarily a cis stereochemistry of the hydrogen because it proceeds in a concerted way. Now we have a 16 valence electron compound. This can accommodate, according to the 18 valence electron rule, an alkene, right? And it does so. So the alkene coordinates, and we form this this 18 valence electron 6-coordinate system, which is very, very sterically congested. And because of the steric congestion, it sort of pushes the formation of this rhodium-3 alkyl intermediate. Remember, when you're doing these catalyst cycles, always do two things. Count the electrons, look at the coordination sphere to make sure that it's not over-congested, and look at the oxidation states to see if it makes sense. So up until now we have rhodium-1, rhodium-1, rhodium-3, that's okay, rhodium-3, but sterically congested, so it kind of makes sense that you're going to have this insertion reaction taking place. Now this is an insertion of an alkene into a methyl hydride. Now remember, we have two hydrides, so what happens in the last step? Reductive elimination, and we form the saturated alkane. Now remember, for the reductive elimination to take place, the H and the alkyl group have to be mutually cis. And that's precisely what I've represented there, and we have this reductive elimination. Now this reaction with hydrogenation of an alkene employing this catalyst is widely studied, and there is experimental evidence for all of these intermediates, essentially. So it's a highly studied and investigated process, and a beautiful reaction involving beautiful classical inorganic chemistry. Yeah, so are there any questions concerning this cycle? So, very important contribution, 1966, by Wilkinson, and I think we will now take a 10-minute break. We will reconvene at 10 minutes past for more exciting
chemistry.